Alright, we were in chapter 10, which is the first chapter of semester 2 in chemistry, and this chapter focuses on energy. So we start this first slide with just the definition of energy. It's symbolized with E, and it means the ability to do work or produce heat. And if you had physical science, you will recognize the two types of energy. The first one is potential energy, which is energy due to position or composition. So get it, P potential, P position. That might help. And an example is what I have in that picture. That picture is Hoover Dam. And this is an example of potential energy because the water behind the dam is ready to do work. And then when it does flow, the work that it does, it creates electricity. But right now, if the water is not flowing, it's being stopped by the dam. That is potential energy. Okay, the next type of energy is kinetic energy, which is energy due to motion. There is a formula associated with this. It's 1/2 mv squared. But you don't need to know that for this chapter, but I'm just letting you know there is a mathematical equation, and I believe it's m for mass and v for velocity. What I wanted to show you are my two examples here. These are athletes in motion, which is a perfect example of kinetic energy. So on the left, just a little shout out to our Olympic Games this winter. You have a skier who's in motion, and then there's a shout out to the best sport ever, my sport. That is a gymnast. That's actually a very famous gymnast on the bars. So both of these are athletes in motion showing kinetic energy. Okay. Now, you might recognize this law of conservation, and we did talk about this in semester 1, but now we're talking about it in terms of energy. So it's the same deal. You cannot create or destroy energy. It's just converted from one form to another. And you do have a space on your notes. I wanted you to draw in the example of the roller coaster because it does show you the two types of energy. So at the top of the coaster in the left-hand picture before you head down, this is considered potential energy because you're ready to go, but you have not gone through the ride yet. You're just right at the top. And then on the right-hand side in this picture, you have people going down the coaster, which of course becomes kinetic energy as you enjoy the ride. So I would draw a picture of this and show one section of the coaster with potential energy and another section with kinetic. Okay, now this page is the most important of what I will go over today. It's all the definitions for this chapter, and a lot of people tend to use these words interchangeably or not really know what they mean, so you should pay attention to this page. So we have energy, which we already described as the ability to do work or produce heat. All right, work. Work is not like going to a place to do a job. I mean, it is, but in the chem world, it means a force acting over a certain distance. And that's also used in the physics world. And there is energy that is transferred when you do work, and that's transferred as heat. And this is an important definition here. Heat is the flow of energy that is due to a temperature difference. So a lot of people say that they're hot or they're cold, and they really don't know what's going on. So heat itself, it is a flow of energy because some temperature change has occurred. And if you've ever heard of thermal underwear, it's underwear that's meant to keep you very warm. It's coming from this. It's thermal energy, okay? And what is this? This is energy that is transferred from a hot object to a cold object by heat. And it's very important that you understand that direction. So energy, thermal energy, is transferred from a hot to a cold object, not the reverse. And you'll be doing several labs with this, and you'll be measuring this heat transfer by temperature. And now, understanding temperature, okay, this is not just some number on a thermometer. It is, but you have to know why that number is occurring. So temperature is a measure of random motion of components of a substance. So the hotter something is, the more motion that it's undergoing. So if you just think of water boiling versus water that you're drinking out of a fountain, the boiling water has bubbles, right? And it starts moving, and that's because it is hotter. So the hotter it is, the higher the temperature, the more motion it has. So random motion equals thermal, right, heat energy of an object. Okay, now this I wanted you to try on your own. So I'm not going to give the answers to this. They'll be provided on the next slide, but I wanted you to try this before I fill this in. So right now we've had a pretty bad stretch of cold weather. The temperatures have been the lowest that I have seen in quite a long time. So we've been in the negatives. School was shut down for a couple of days, so it was pretty cold. So this example is perfect for this time right now. This is a winter's day, and we have snow on the ground. But right now, at the time that I'm recording this, our temperature is starting to rise. So let's say it rises from 10 degrees Celsius in the morning to 40 degrees Celsius in the afternoon. So my question to you is, what happens to the snow? Now, it may seem obvious. In fact, the same word is used a couple of times, but see if you can fill this in before I show you the answers. Okay, so I do hope that you paused this and try to fill in the answers yourself. But what does happen is that it melts, right? The snow melts. That wasn't difficult. But why it melts is due to heat transfer. And snow is water, right? And water will absorb heat from the air. So there's the transfer from the air to the water, causing the snow to melt. And then snow molecules, this is important now, if the temperature is going up, it means they're moving faster as they melt. Okay, and this is just an explanation of what we just went over. So melting is motion of the water particles, and that is because heat is transferred from the air or the atmosphere to the water itself. They are absorbing that heat, the particles move faster, and the state of matter changes. Okay, now these two words will look familiar if you've had physical science, exothermic and endothermic. Okay, before we talk about those two processes, I want to just mention system versus surroundings. So these are basically, for the chem world, it's our chemical reactions. But when you talk about physics or other areas, they use the term system and surrounding a little bit more. System is part of the universe we focus our attention on. And if you look at the example, that's a chemical reaction, so it's basically what you would do in lab. And then surroundings are everything else in the universe. So maybe in this reaction, did some heat come off, or was there a color change? So it's whatever is not the actual reaction itself, but maybe what is produced from it or something that you've seen. Those are the surroundings. Okay, so just very basic terms. Okay, now exothermic. These are the reactions that you like to do best in lab. This is where energy flows out of a system. Heat is released, and if you look at that picture, a good example is combustion or fire, right? So take a look at my example. If you strike a match, right, potential energy in the chemical bonds is converted to thermal, right? So potential to thermal. So my question is, before I tell you, as you strike the match, what happens to each type of energy? So what happens to potential? Does it go up or down as you strike it? And to thermal, as you strike it, does it go up or down? So I'll give you a chance to think about it before I tell you. Okay, the match by itself had potential energy, and as you strike it, potential energy decreased. But thermal energy is heat, right? That's the fire, so that increased after you struck the match. Endothermic is where energy is absorbed from the surroundings, and a perfect example is an ice pack. If you've ever had one where you have to squeeze it or step on it to make the two chemicals mix inside, and when they mix, it becomes cold because the chemicals are absorbing energy, and you feel it as cold. Okay? So this chapter is the study of energy, and another term for that is thermodynamics. And the first law of thermodynamics, I'm just telling you there's a different name for it, it's the law of conservation of energy, which you already talked about. So make sure you remember this is an important law. Energy of the universe is constant. And the two types of energy that remain constant are potential and kinetic. So you have each of those in a system. Alright, and I leave you with our first unit of energy, because we're going to talk about some food right now. Calorie is, with the lowercase c, the amount of energy you need to raise the temperature of 1 gram of water by 1 degree Celsius. So it's a tiny little bit of water, has its temperature increased by 1 degree Celsius. That is the lowercase c calorie. Now, the capital letter C, or food calorie, is really a kilocalorie, or 1,000 times the little c calorie. So this is what you see in food, and that's why the handout that went with this lecture, we started to look at different amounts of calories in different types of foods. And you'll also do a lab on this later on.